All right, so we're back here. I've actually put some information here in writing that will help to kind of differentiate the sine waves that we typically are working with in industrial drive applications. So here, as you notice, I've drawn an AC sine wave. This waveform is considered sinusoidal. And this is what it would look like if you had an oscilloscope connected to the power that's being fed to an AC induction motor. Sorry, I'm stuttering here. So it would be a nice smooth analog type sine wave, as you can see here. When you just apply across the line, voltage and current to an electric motor. So in the United States, we use 60 cycles per second. That means that the voltage and the current are actually alternating back and forth. So we go one direction and we change direction 60 times per second. Okay, this here would be considered a half wave at this point. If we go all the way down to here, from peak to peak, that would be one full cycle. Okay. So as you notice here, I drew these lines. What those lines represent is the true RMS value of the voltage. So here you see peak voltage is at the very top. Basically the distance from here to here, that part of the sine wave really has no effective value. It's pretty useless. So if you were to take the equivalent heating value, DC, which is direct current, the equivalent direct current value, this is the peak voltage. Now if we multiply that voltage times 0.707, that's going to give us this line here, which is true RMS value. Now most digital meters are actually going to measure the true RMS. They do the calculation for you. But as you noticed earlier when I was taking readings from the output of the drive, I was seeing a higher voltage. Okay, I'm actually measuring some peak voltage here, and that's why I ended up having to change my range to 1,000. And by doing that, it's allowing the meter to see the DC heating voltage. You notice here we have an inverter sine wave, which is what I'm actually looking at right now, and I'm trying to take measurements. The sine wave looks a lot different. It's a lot of rapid pulses that the inverter creates. It actually takes DC voltage and creates a kind of a false AC sine wave, and you end up having these rapid digital pulses as a result. So that's why it's really important that you use the correct meter. A Fluke 87 really is the ideal meter for HVAC techs if you're doing commercial industrial type work. So therefore, another term I want to talk about is DC bus voltage. So the inverter actually takes AC, converts it to DC. You're going to have a DC bus that's going to have a high voltage on it, a high potential. And I've actually found the measurement here in the drive. See if you can see that. 651 volts is the DC bus voltage. So that voltage, as you see here, DC bus voltage should be the actual line voltage multiplied by 1.414. Okay? So it's important to kind of take these readings, when you're doing your maintenance. And you want to know if the drive is actually, if it has an issue with filter capacitors. That can be an indication. If you have a low DC bus voltage, you may have a drive problem. So anyway, I hope this is very helpful to you, and so we'll just see what comes up in the next video. I'll try and elaborate a little deeper. Thanks.